Yeah, great. So yeah, so I'm Shangtong. I'm a PhD student at Oxford. So previously I did my master here with Rich. So today I'm going to present a Generalized Off-Policy Actor-Critic. This is a joint work with Wendelin and Simon. So let's start with Off-Policy Actor-Critic. So Off-Policy Actor-Critic is the off-policy version of the famous actor-critic algorithm. Basically, it tries to maximize the excursion objective. Here I use J-mu to denote the excursion objective. Mu is the behavior policy, and pi is the target policy, and d-mu is the stationary distribution of the behavior policy. So I assume the MDP induced by the behavior policy mu is ergodic, so d-mu is unique. Basically, the excursion objective measures the value function v pi with the stationary distribution of the behavior policy. There are many algorithms optimizing this objective. For example, at the very beginning, we have our off-policy actor-critic or off-pack from degrees, and we have off-policy DPG, and we have DDPG. We have actor-critic with experiment replay. We have off-policy expected policy gradients, and we have impala. More recently, we have emphatic actor-critic and actor-critic with emphatic weightings. So we have been optimizing this excursion objective for 7 years. Now I think it's a good time to pause and ponder, do we really want to maximize this objective? Let's start with a very simple MDP. This MDP consists of two circles. Basically, there are rewards plus 10 and plus 5. So other rewards are always 0. And the agent only needs to make a decision in one state, state A. It can either go to state B or go to state C. Say the behavior policy mu is random, so it means it goes to state B with probability 0.5, and it goes to state C with probability 0.5. And let's see what will happen if we try to maximize J mu. So because the behavior policy mu is fixed, so its stationary distribution d mu is fixed, so we can do nothing for d mu. We can only change v pi. Because of the discounting, we set the discount factor to 0.6. So which means the value of the state B is almost always 3.6. It doesn't change no matter what pi is. And the value of state C is always 5. Which means we can't change the value of B and we can't change the value of C. All we can change is the value of A. So we want to maximize the value of A. Then we will go to state C because C has a higher value than B. So when we try to maximize this excursion objective, we end up with staying in the inner circle. It's obviously something that we don't want because the reward is only plus 5. What we really want is to stay in the outer circle. This will happen if we try to maximize the alternative life objective, which is this J pi. So in this J pi, we measure the value function v pi with the stationary distribution of the policy pi itself. So in on-policy setting, if we try to maximize this alternative life objective, it's equivalent to maximizing the average reward. So it's clear that the J pi maximizing policy will stay in the outer circle. So the problem is it's hard to maximize this objective because it has a stationary distribution d pi, but the agent is following the behavior policy mu, so we can't sample from d pi, we have to sample from d mu. That's why this objective is hard to optimize, but it's unbiased. It gives what we really want. We want to maximize the average reward. So the excursion objective J mu is biased, but it's easy to optimize because we can sample from d mu. The alternative life objective is unbiased, but it's hard to optimize because we can't sample from d pi. So this is not the first time we face this dilemma. For example, we have TD0 and Monte Carlo. The bootstrapping target for TD0 is biased because it's an estimation, but it has lower variance. The bootstrapping target for Monte Carlo update target is unbiased, but it has larger variance. So we end up with TD lambda. We introduce a new parameter a new hyperparameter lambda to do bias variance trade-off. So similarly, we want to unify the alternative life objective and the excursion objective. We want to introduce some new hyperparameter and unify the two objectives together, and we can do some bias variance trade-off. So we achieve this by considering a unifying transition matrix introduced by Glad and Bellemare. So this transition matrix is, we use P gamma hat to denote this new transition matrix. If the agent follows this transition matrix, it can either follow the behavior policy and go to the next state with probability gamma hat, or it will be reset to the stationary distribution of the behavior policy with probability 1 minus gamma hat. So it's clear that if this gamma hat is 0, then P gamma hat is just d mu. And if this gamma hat is 1, then P gamma hat becomes P pi, the transition matrix of the target policy. So it seems to be the unifying matrix we want. Glad and Bellemare also show the stationary distribution of this unifying transition matrix. So when gamma hat is smaller than 1, they give a closed form solution for d gamma hat. Here, d gamma hat is the stationary distribution of this P gamma hat. When gamma hat is equal to 1, so it's clear that d gamma hat is just d pi because P gamma hat is P pi. But the problem is we don't know whether d gamma hat converges to d pi when gamma hat approaches 1. To say this, we can have a look at the expression of d gamma hat. When gamma hat approaches 1, 1 minus gamma hat approaches 0. And because P pi is a transition matrix, its largest eigenvalue is 1. So when gamma hat approaches 1, I minus P pi is no longer invertible. So basically, the limit when gamma hat approaches 1 is something like 0 over 0. It's not clear what it is. If it's a scalar, we can use L'Hopital's rule to compute the limit, but it's not a scalar, it's a matrix. So it's not clear to use L'Hopital's rule to compute this limit. So I will address this issue later. So what we propose is a new objective. We call this the counterfactual objective. This objective unifies the two old objectives. In the counterfactual objective, we measure the value function V pi with the stationary distribution of the unifying transition matrix. So V pi is measured by d gamma hat. So when gamma hat is 1, it can recover the alternative life objective. When gamma hat is 0, it recovers the excursion objective. But still we have the problem. We don't know whether the counterfactual objective converges to the alternative life objective or not. So if it doesn't hold, it means the counterfactual objective may not be a good objective because the distance between the counterfactual objective can be very large from the alternative life objective. So in that case, we may not prefer this objective. But fortunately, we are able to prove that the counterfactual objective converges to the alternative life objective. So we first introduce this matrix in capital pi gamma hat. So each row of this matrix is just the d gamma hat. And we can, because P gamma hat is a transition matrix, the power of a transition matrix converges to the stationary distribution. This is a standard conclusion for ergodic MDPs. And we compute the limit when gamma hat equals to 1. When gamma hat approaches 1, this step is also easy. Now we assume we can interchange the two limits. Then we compute the limit when gamma hat approaches 1 for P gamma hat to t. This limit is P pi to t. It comes from the definition of P gamma hat directly. And then we use that standard conclusion again. And we get d pi t, the stationary distribution. So it shows if we can interchange the two limits, we are able to show that d gamma hat converges to d pi. So now the problem is whether we can interchange the two limits or not. So this is our first theoretical results. We prove that the power of P gamma hat converges to the stationary distribution uniformly. Note here, the standard conclusion is a pointwise convergence, which means this convergence is true for each gamma hat. For each gamma hat, we can find a bound to control the distance between p gamma to t and capital pi hat. But our result is more stronger. We prove this convergence is actually uniform, which means the bound doesn't depend on gamma hat. For any gamma hat, we can use a same bound to control the distance between p gamma hat to d and capital pi gamma hat. So with this uniform convergence, we can invoke Moore-Osgood theorem to interchange the two limits. So now, because we can interchange the two limits, we show that the d gamma hat converges to d pi, and the counterfactual objective actually converges to the alternative life objective. So it's indeed a good objective. So now let's compute the policy gradient of the counterfactual objective. So counterfactual objective is j gamma hat. It's defined as summation over s, d gamma hat s, and v pi s. Because our agent follows the behavior policy, if we want to sample something, we need to introduce the stationary distribution d mu. So we introduce this d mu and this density ratio d gamma hat over d mu s. So I will use a shorthand C to denote this density ratio. So C, obviously C also depends on gamma hat, but I just ignore this dependency for the sake of clarity. Then we compute the policy gradient. We compute the gradient with respect to the policy parameters. Simply, we can use the product rule of calculus. So we have the gradient of j gamma hat consists of two parts. The first part is easy. We can just get that gradient by set the interest function to C in the eighth paper. Then we can get the first summation for free. The real problem is the second part. In the second part, we need to compute the gradient, the policy gradient of a ratio, the policy gradient of a state distribution. This part is the hardest part. Fortunately, Gad and Bellemere also have some other results. They show that the density ratio C satisfies this equation. This is true for all the behavioral policy and all the gamma hat. They also propose some stochastic approximation methods to learn the density ratio C using this equation. So in this talk, I will assume C is available. We have access to C because it can be learned by stochastic approximation. Then how can we get the gradient of C? We just taking gradients of the policy parameter in both sides of this equation, and then we do some algebra manipulation. Finally, we get the gradient of C. So now we have gradient of C, and the first part comes from the eighth paper for free, and we have the gradient of C. So now we have computed the policy gradient of the counterfactual objective. The next problem is to sample that policy gradient. So the first summation is also easy because we can use the techniques from the eighth paper to sample that. The problem is how can we sample this gradient C? At the first glance, it seems prohibiting because we have that inverse guy. It's not clear how to sample it. But if you're familiar with ETD paper, you may be familiar with that inverse guy. We can use similar techniques from ETD paper to get some unbiased sample of that inverse. And the remaining parts, the gradient p pi, d mu, and c, can be interpreted as a special interest function. This interest comes from the algorithm itself. It's different from the user-defined interest in the ETD. So we call this interest an intrinsic interest function. But we still need to sample this interest function. Then we can borrow some techniques from COFTD, which was proposed by Hawk and Scheinmeier years ago. So due to time limit, I can't explain all details how to sample this guy. But the core idea is to combine techniques from ETD and COFTD, so we can get a sample for this gradient. Now we are ready to compute the gradients. For the second summation, we can use the previous mentioned techniques from ETD and COP-TD to get an unbiased sample for the second summation. So this ZT2 is an unbiased sample for the second summation. Here C is the density ratio, and we assume it's available because we can learn it. Just like we learn value function, we learn this density ratio. And for the first summation, we use techniques from the ACE paper. And we can show ZT1 is an unbiased sample of the first summation. And we sum them together. This is our second theoretical results. We saw that when t goes to infinity, ZT1 plus ZT2 is an unbiased sample of this policy gradient of the counterfactual objective. So here is some experimental results. First, we test our algorithm JeffPack in the two-circle MDP. Let's see whether it can find the optimal solution as promised. So we compared JeffPack and ACE. So the x-axis is the training steps, and the y-axis is the probability of going to B from state A. It's clear that as training progresses, ACE converges to a policy that always go to state C, but JeffPack converges to a policy that always go to state B. This is within expectation, because if we try to maximize the excursion objective, we must go to C. But if we try to maximize the alternative life objective, we must go to B. We also study the influence of Gamma Hydra in JeffPack. The results are shown in the right figure. We can just ignore that lambda 2. That lambda 2 is also a hyperparameter for bias variance trade-off, but it's not useful now. It's clear that when Gamma Hydra is larger than 0.5, JeffPack can find the optimal solution. But when Gamma Hydra is less than 0.5, JeffPack will end up with the same solution as ACE. So JeffPack also scaled up to challenging deep reinforcement problems. We benchmarked JeffPack, ACE, and Off-Pack in several Mujoko robot simulation tasks. The behavior policy is uniform random policy, and we want to learn some meaningful policy from a random behavior policy. It's clear that JeffPack outperforms ACE and Off-Pack with a large margin in 3 out of the 5 tasks. So we also compared JeffPack with another popular algorithm, DDPG, in these benchmarks. So the behavior policy is still random. In this case, the advantage is not very clear, but in 2 tasks, in the hopper and the swimmer, it can be seen that JeffPack boosts performance a lot from DDPG. So that's all. The paper is available at arXiv, and thanks for questions. Yeah, bowling.
Can you go with your inner outer circle? I feel like I got lost on something fundamental. If gamma equals 0.6, the right answer is to go on the inner circle.
Isn't it true that those values are the values given the discounting rate of 0.6?
Yes.
And so, of course, they won't be the right decisions for an undiscounted objective, which is what you're going to evaluate them by, right? You're going to ultimately evaluate it by the average.
If you then proceed to evaluate with the average reward as the objective, then the right answer. If your goal is to maximize average reward, it's to go around the outer circle. I guess I'm just confused. I don't understand this whole distinction between the alternative life objective. You're saying it's going to choose the wrong thing. What is going on? It's like you change the discount factor underneath it or something? If the discount factor is 0.6, the optimal behavior
It still goes to
the inner circle. When I'm at A, if I look at maximizing my discounted return, if I go to B, I get a discounted return of 3.6 plus some more because you actually go around the loop a few more times, but 0.6 to the 8 or something is going to be very small, so a little bit, only a little bit added. Or I could get 5. I feel like I'm missing something very fundamental here. Because obviously, like you just showed me, hey, I have this cool algorithm, and now it gets the outer circle. I wanted to do the outer circle, but I'm stuck because I think I want the inner circle.
It's still not clear to me why when gamma is 0.6, the optimal solution is inner circle.
Well, because it's the sum of your reward on the next time step plus gamma, the reward of the time step after that, plus gamma squared of the reward time step after that, and so on. And in the one case, I could wait 4 steps and get 10, which will be gamma to the 4 times 10. Or the other case, I can wait 1 step and get 5, which will be gamma times 5. The optimal return, the policy that maximizes my return at the one decision point I have in the entire MDP is to go to C.
Yes, in episodic setting, if we want to maximize the return from A, the optimal solution is to go to the C. But if we consider the average reward, we should go to...
Average reward means there's no discount factor. I don't understand. You're mixing two things in a way. I mean, maybe this is my fundamental misunderstanding, is I don't understand.
So I think maybe I can answer your question.
Please.
I think what Shangtong is saying here with the alternative life objective is that the alternative life objective for any constant gamma is actually the average reward objective. So if you had started with the discount factor and you considered the alternative life objective, you're really implicitly considering the average reward objective.
Only if, I mean, okay. I thought when you think about discounting and you were to try to define, I have discounting, now I want to write out a policy gradient objective. I thought, okay, so to write out an objective, I'm going to need to define some distribution over start states. And then I could still define d pi, but d pi would be the sum of discounted distribution rates over start states. And that's what d pi is. It is not itself a distribution, it doesn't sum to 1 over states. It is this funny thing that says how much weighting will I get from the start state of my discounted objective. In which case, then those two things are equal. I think here the d pi s is something else. D pi s is now truly the visitation rate.
I think so.
Yeah, so it's not episodic case.
But then v pi is now this discounted one.
Yeah.
Yes, because in the
Sure, so this is all wrong.
off-policy version, v pi is discounted. So I just consider a discounted value function even in.
Okay. Okay, I'm beginning to see an inkling of something, but then I'm seeing an inkling of, yes, you applied an objective in a nonsensical way and got a nonsensical result. Now maybe you fix that.
I found it very confusing for this because if I just look at this JMU, like you don't care about where mu come from, we know that if you don't limit your policy space, you can put arbitrary initial distribution there, and you will always get optimal policy. So the limitation that what limits you not able to get the optimal policy for the discounted problem is policy gradient would be the space, the subspace of policies you consider. In that case, I mean, if it's the full space, then whatever d mu you put there, you will get the optimal. It doesn't matter as long as d mu is positive for all state. So when you finally say, okay, this one can't give you the optimal, the other one can give you, then it must be there's some approximation limited in the subspace of policies.
Yes, I. Yeah, because this JMU will give the optimal. So if we use policy gradient, it will to maximize this JMU, we will end up with an optimal solution to maximize an optimal policy to maximize JMU. But in this case, it's clearly not what we want.
It doesn't matter what DMU you put there, you will get the optimal policy for all states for the MVP. As long as DMU is positive for all states. Because your V pi is a discounted problem, right? It's the discounted value. So as long as you put the initial weight for all states is positive, you have to improve it. Like however you can improve for one state, you can improve the whole objective. So I didn't get
Yes, so
I would actually ask a follow-up question for Jing. Do you mean in the case where you have the tabular setting, like no function approximation?
Yes.
Right. I think these objectives are only somewhat interesting if you do have function
Yeah, but then
approximation.
you have to say, in this case, you cannot get optimal. In the other case, you can. Then it's not just say what weight you put there, right?
yeah.
You have to do what space you limit them. Like if it's in where you consider a subset of policies and the other objective has advantages, then you have to say why it has advantage when you consider subspace of policies.
Yeah.
I think maybe from my understanding, I feel like at one point you're missing like that v pi s depends upon a choice of gamma.
Yes.
So we might think about parameterizing that by gamma as well as pi. So pi and gamma affect v pi s. And d mu s, I think you're choosing to use a different gamma there. And then this mix you're observing doesn't work. There is a way to define the distribution, the visit distribution under a discount. And you're choosing to use no discounting there, putting discounting on the other one, and say the objective when you mix them together produces this weird result.
Yeah, but this is from that off-pack paper. They use that undiscounted state visitation.
Okay, maybe I'm saying that paper's wrong. I don't know. I'm fine. We can
Yeah.
look this up.
Another comment is that you chose that you have an example, say d mu is not good, but there certainly will be examples that d pi isn't good, right? I think the balancing is.
Yeah, but when
d pi doesn't even need to exist, right? Because you solve the discounted problem. Why do you want it to have a ergodic Markov chain? So there are cases you don't like for some problems, discounted problems, you don't really require, right? You don't, or for many problems actually, you don't need the high induced irreducible Markov chain. It could just be absorbed in one state, and that pi would be very bad, right? Here you would have to assume all the policy pi in this discounted problem induce irreducible Markov chain.
yeah, because I'm considering continuing setting, so it's
What do you mean by continuing setting?
like there is no beginning and no end. There is not an observing state.
Still, there's it could be, say, it could be absorbed in a subset of states. It could have transient states, right? It could get absorbed in a subset state, but not in a fixed absorbing state, right?
Yes.
So then
Then we don't need to care that transient states.
But the objective would be different. Like if you don't care about, so you set up a discounted problem, that's because you care about the transient behavior. The objective v pi is discounted, so you care about the transient behavior. So there is the differences. Right? Like I care about the first 100 stage. If I care about the asymptotic performance, I would start with an average reward problem, right? I would have my v pi actually be the average reward.
Yes.
So yeah, so I think so d pi, even if you consider the things that never get and that doesn't terminate, still even if you have a subset of states, you still d pi the distribution. D pi can be very different from the behavior of your policy, like say the first 1,000 stages. They can be very different. So you need to take into account these factors. It's not just say d mu is always bad. But d pi would have its own problems.
Yeah, but if you try to actually change your policy and follow the target policy you learned, what you finally care is d pi, not d mu.
I'm saying d pi, you still consider the invariant distribution induced by the Markov chain.
Yeah.
Not the pi. But your v pi is a discounted problem. So if you consider the what they call visitation, state action visitation, and the pi that considers the transient period because you're setting up a discounting problem. That one would be very different from your final the stationary distribution. So even if you consider that, you still need to consider d pi, the relation between d pi and the behavior of the policy.
Yeah, it's kind of, yeah.
You guys should have a meeting about this. I'm going to ask a different question. So in your experiments, you're comparing ACE and your new method on some continuous control tests, I think?
Yes.
And I guess that ACE probably hasn't been applied to any of those tests. So how did you tune the parameters and make sure everything's fair?
Yes. I tune ACE first,
So
then...
you did like a systematic sweep, you tried many different values.
No, I can't do grid search for every hyperparameter.
So how did you ensure that it was fair?
Oh. So I first tune off-pack by experiments, and then I tune ACE. So because ACE and off-pack have many similar parameters, then my ACE implementation inherit the hyperparameters from off-pack. And in ACE there are some extra parameters. Then I do some grid search for those extra parameters for ACE. Then I do grid search for more parameters for Jetpack. Yeah, Eric?
For ACE, what was your setting for the interpolation parameter, the lambda A?
You mean lambda?
I remember in the book, or sorry, in your paper, it showed that you used lambda equals, like lambda A equals 0. Do you call it lambda 1 or lambda 2?
Lambda 1.
Okay, you said that equals 0, right?
In the
paper,
in this two-circle MDP, it's 0, but here it's not 0.
okay.
It's 1, I think, something like that.
I think we're out of time. I have one last question. Are you using stochastic policies?
Yes.
What are they? Are they like Gaussian distribution?
Yeah, Gaussian distribution. Yes, Rich?
How many runs are these results averaged over?
10.
10.
And the shadowed region is standard errors.
And you're showing the standard error from only 10 runs.
Yeah.
And you were my student. I could never do that.
Yeah.
What about in terms of like your evaluation? You're evaluating how many times do you run it in the policy at like each step?
Oh, I do evaluation for 20 episodes to get that JPy.
I think time's up.